find the electric field at location A. Give the magnitude of the electric field and the direction that it's facing. All right, and we've got 4 charges here. We have some positive charges, and there's one negative charge in the mix. And I'm hoping that you notice that there's a lot of symmetry going on in this problem. Look for that when you have these kind of problems where you've got charges placed all over the place. Look for symmetry because there's lots of opportunities for shortcuts usually. When there aren't shortcuts, the problems get pretty long, so a lot of teachers usually include shortcuts on their tests and stuff. But here's the really important thing to know. Now, in order to do that, it might be helpful to know exactly what the electric field is. So I got it defined for you. The electric field tells you what the force would be on a +1 Coulomb test charge at that location. If we want to find what the electric field is at location A, all we have to do is just pretend that there's a +1 Coulomb charge there. So let's do that with the 3 easy steps of finding electric field. So to break it down, anytime you want to find the electric field at a given location, there's 3 easy steps that you got to do to pull it off. First, imagine a +1 Coulomb charge at that location. So for a moment, we're just going to pretend that there's a +1 Coulomb charge at location A. Second, just find what the net force on that charge would be, and you've got your electric field. I guess that's only 2 steps, so maybe for step 3 you can eat a sandwich or, I don't know, go outside, play some basketball, whatever you want to do. You got to mix it up a little bit. You can't do physics all the time. It's not good for you. Okay, so all we really need to do is just find the net force on that stinking charge, and then we've pretty much got the problem solved. So let's work on that. So if we want to find the net force on our imaginary +1 Coulomb friend over here, then all we got to do is draw a force diagram just like before. So keep in mind that likes repel and opposites attract. So if A is a +1 Coulomb, then this one is pushing down on it, this one's pushing up, this one's pushing to the right, and this one's actually pulling to the right because it's a negative charge. So the force diagram looks something like this. And oh my gosh, these two cancel, which means I don't even really feel like calculating them. We actually could care less what the forces are that are coming from these red ones because they cancel anyway. Don't waste your time. Also, hopefully you looked at the symmetry and you noticed that these two were the same charges and the same distance apart, which means all we really need to do is just find either F3 or F4 and simply double it. So something that probably looks pretty crazy is actually not very intimidating at all, and it looks like we're going to have plenty of time to eat our sandwich. Okay, so if the net force is simply 2 times the repulsion force from the green one here, then to calculate that, we just use this formula that the Coulomb force between 2 charges is K times the first charge times the second charge divided by R squared. And K is just 9 times 10 to the 9. And it's really just a matter of throwing those numbers in. So 2 times K times the green charge times our imaginary +1 charge friend, which makes the math nice and easy, over R squared. And you end up with 216,000 newtons per coulomb, which means for every coulomb of charge you add, you get this many more newtons of force. Don't let the big number worry you. A coulomb is a whole lot of charge, so it's not a big deal. And it asks for direction as well, so the direction is going to the right on this one. All right.